Okay, today we're going to talk about Unit 4, Building Block 4. This covers nuclear chemistry. Your learning goals are to be able to describe the characteristics of alpha, beta, and gamma particles, and to be able to balance nuclear equations. Before we get started though, I want to talk about the difference between the nuclear reactions that we're about to cover and chemical reactions that we're going to be talking about for the rest of the year. So the difference here is that nuclear reactions create new elements through either decay, fusion, or fission. But the chemical reactions that we're going to be talking about for the rest of the year really are more focused on rearranging atoms into new combinations to create new compounds or substances. But they don't change an atom's identity. So they won't take one element, atoms from one element, and turn them into atoms from another element. So that's the big distinction here. Nuclear reactions will change the identity of an element by changing, the composition of the nucleus, but chemical reactions will not change the nucleus of an atom. They just all we're doing here is rearranging atoms in a chemical reaction. Okay, but regardless of what type of reaction we're talking about, neither type of reaction creates or destroys matter. Okay. So what is radioactivity? Radioactivity is various types of emissions from the nucleus of an atom that can be due to several different factors. And when I say emissions, this means just things that are ejected from the nucleus of an atom or thrown out of the nucleus of an atom. So the first factor is an instability in the nucleus resulting from having too large a mass. So if an atom's nucleus becomes too large, then it starts to become unstable. And we'll talk in just a few minutes about why that might be. The second one is that it can be caused by a deviation in the ratios of protons and neutrons from what's called the magic numbers. And I'm not really going to mention the magic numbers again because we don't really need to know a lot about those. But we do need to know that there are some ratios between protons and neutrons that are more stable than others. You don't need to know specifics about that. Just know that sometimes an atom might have, too many or too few neutrons, and it would need to adjust that. Whatever the case, though, atoms always undergo nuclear decay in order to achieve a more stable nuclear configuration. Also, all atoms with nuclei larger than 82 atomic mass units are radioactive by nature. So here's a chart just kind of describing the different types of radioactive decay that we can have. There's alpha decay. This is a type of decay that results from an alpha particle being ejected from the nucleus of an atom. And these are the two symbols that we can use. These symbols are interchangeable. Remember before when we were talking about Rutherford's experiment and we said that an alpha particle is equivalent to the nucleus of a helium atom. So we take a look at the periodic table right here. We've got helium up here in the corner. You'll notice that helium has 2 protons and it's got an atomic mass of 4. So it's got 2 protons and 2 neutrons. So let's take a look back here at this chart again. We could write the nuclide symbol for helium. This also can represent what an alpha particle would be, or you might also see just the alpha symbol with the same numbers from the nuclide symbol. The mass of an alpha particle is 4 atomic mass units. We've got 2 protons, 2 neutrons. It is not very penetrating a particle. Alpha particles tend to be pretty large, and 2 protons and 2 neutrons compared to other types of radiation is fairly large. And it also has, or alpha particles also have a positive 2 charge associated with them because of the 2 protons. Beta particles are a type of radiation resulting from the emission of a high energy electron from the nucleus, and you heard that right, electrons coming from the nucleus of a radioactive atom. And we'll talk more about what's going on with that when we get to the slide specifically for beta radiation. The symbol for the symbols that represent beta particles, we could have this beta symbol here. And then again, just like on a nuclide symbol, we would have the mass up here. So they have no mass, it's an electron. The mass is so little that we just kind of ignore it. And then we've got, this represents the change in the number of protons here. So we're going to talk about why that's a negative when we get to the slide again. So we could either write the beta particle symbol like this, or we can just say it's a little electron and use an E to represent the fact that it's an electron, and then use the same numbers. There is no mass associated with this, and because these particles are so tiny and they have no mass, they're better at penetrating things than an alpha particle is. Another reason they could be better at penetrating materials is that their charge is not quite as much as it is for an alpha particle. An alpha particle has a +2 charge, so the magnitude of that is 2, and the magnitude of the charge here for a beta particle is 1. So it's got about half the amount of charge. Even though it's an opposite charge, we're just thinking about the size of the charge here. Gamma radiation, it often occurs after beta decay has occurred, so it could occur after this, but there's a specific type of beta decay. And it's really just the release of electromagnetic radiation, which is a form of light. It's just a release of energy in the form of light from the nucleus of an atom. And we just use this little beta symbol. Sometimes you'll see people use a nuclide kind of configuration where we've got a mass and an atomic number, but there's really no mass or no atomic number, so you'll see 2 zeros right there instead. But you could just write a gamma symbol like this. This is the most penetrating type of radiation because it is extremely high energy and it's got very tiny wavelengths, so it's very, very penetrating. It's very hard to block gamma radiation, but it has no charge as well. And we'll talk more about gamma radiation here in a minute on that slide. So the first thing we're going to talk about is alpha decay. And alpha decay occurs when the nucleus of an atom is too large for the strong nuclear force to hold it together. So we're all kind of familiar with what gravity is. Gravity, when it's around large, massive objects like Earth, kind of holds things together. It pushes things down towards the center of gravity. But when we're talking about things on the atomic scale, we have what's called the strong nuclear force. And the strong nuclear force is what's holding all of those positive charges together in the nucleus. So we talked before about how, electrostatic attraction occurs between two oppositely charged particles, and how the electrons are staying away from the protons, or I'm sorry, they're not staying away. They're being held away because of the amount of energy they have. But now I'm talking about, if we really think about it, the nucleus is a bunch of protons all together. And that strong nuclear force is overcoming that electrostatic attraction that's trying to make those positive charges repel each other and holding them together. So it's a very strong force, but it only acts on very teeny tiny distances, like the diameter of an atomic nuclei. If an atomic nuclei becomes so large, about as large as most of the radioactive elements, above a mass of 82 atomic mass units, then the strong nuclear force has a hard time holding that many protons over that distance together, and that gives that atom's nucleus some instability. And in order to counteract that instability, an atom can eject an alpha particle, which is 2 protons and 2 neutrons, from its nucleus to gain a little bit more stability, become a little bit smaller, and allow that strong nuclear force to act a little bit better on its particles to hold them together. So again, alpha decay occurs if a nucleus becomes too large. It has to eject some of its mass out, some of the particles, in order to regain some stability. Alpha particles have a relatively low amount of energy. They don't penetrate very well because they're kind of big and slow, but they are very ionizing. And so we talked about what an ion is last class period, and we said that ions are atoms of elements that have a number of electrons that is not equal to the number of protons. We could either have more electrons than protons or fewer electrons than protons. So anything that will add or remove electrons from something else is considered to be ionizing because it's creating an ion. And what happens here when an alpha particle is ejected from the nucleus, it has no electrons. And so it's going to be looking for electrons from the first thing that it comes into contact with. And so whatever it comes into contact with, it's pulling electrons off that other thing. And now that other atom is an ion because it's lost some electrons. So that's why we consider alpha decay to be very ionizing. Each particle would pull 2 electrons to balance out its +2 charge off of something else in its environment. So when we talk about balancing equations with alpha decay, we need to first kind of look at the anatomy of an equation. So if we look over here at this x, az yields y, and then it gives you the little math equation here to be able to figure out the new mass and the new atomic number, and then the alpha particle over here. If we take a look at this equation, we can treat everything that's on the left side of that arrow like it's what we had before the reaction took place. So this is our before, and then this is our after the reaction. This is what we've got left after that reaction happens. We can also look at this as one big math problem if we treat this arrow like an equal symbol. So whatever we have over here is equal to everything that's on this side of the equation. So let's take a look at an example and talk about what happens when an atom ejects an alpha particle. So in alpha decay, this means that the resulting element here, let's say we're starting with radium, it loses 2 protons and 2 neutrons. So that means its atomic number down here, 88 for radium, is going to lose 2 protons, so the atomic number is going to decrease by 2. And the mass number up here, remember mass is protons plus neutrons, so the mass number is going to decrease by 4 because the mass of an alpha particle is 4. And if you look up here, this gives you the little equation here. So the mass of x here minus 4 equals the mass of y. And the atomic number of y is z minus 2. So this z right here minus 2 protons. All right. Uranium is another example. Here's another one. Uranium-238 loses an alpha particle. So that's over here. Now they're separated at the end. And when it loses that alpha particle, it becomes thorium, thorium-234. The mass number is decreased by 4. The atomic number is decreased by 2. One suggestion I have while you're going through this, I probably should have said this earlier, but if you have your periodic table out, the one that you got at the beginning of the year, and you're using it and you're looking to see where these elements are as we're talking about this today, it helps you become more familiar with the locations of elements on the periodic table so that later on during the year, you're familiarized with it, you kind of have an idea where most things are, so you're not spending so much time on a test or on homework searching for elements. All right, so let's go ahead and do some examples. And the first example, we've got lawrencium-256, and it's going to undergo alpha decay. So lawrencium-256 equals something plus 1 alpha particle. So we take that minus 4 from the mass number, so we're going to end up with 252 as our mass number, and we subtract 2 from our atomic number, then we're going to end up with 101. And if you look at your periodic table, atomic number 101 is mendelevium. So we have mendelevium-252. Okay, the next one, we have proactinium, and proactinium is going to give up an alpha particle, and it's going to become actinium-227. So its atomic number decreases by 2, and its mass number decreases by 4. And so take a look at this really quick. On this side of the equation, if I add these two things together, I get proactinium-231. So if you want to double check your work, make sure that these are adding up correctly and you're getting that again. That's one good way to check things to make sure you're doing them correctly. All right, so the next one is we've got actinium-225. Oops, I didn't mean to click that so far. It loses an alpha particle, and then we're left with francium-221. And then down here, we're going to start with francium-211. And that's going to lose an alpha particle and become astatine-207. And then the last one here, we've got gold 185. We're going to take 4 from the mass number and 2 from the atomic number, and we're going to end up with iridium 181. All right, so it's a good idea to put some of these examples in your notebook, and hopefully you were maybe pausing the video in between to see if you could figure these out yourself, because it's good practice. If you have questions, go ahead and write them in your notebook, and on Monday before we play Atomic Jeopardy, I'll try to give some time for questions about this stuff. So the next thing we're going to talk about is beta decay. Beta decay occurs when there's an imbalance in the number of protons and neutrons in the nucleus of an atom. So in this case, an atom has too many neutrons too many neutrons in order to remain stable. So at the beginning of this recording, we talked a little bit about how there's some magic numbers or magic ratios of neutrons and protons in the nucleus of an atom. And there is some variation from those ratios that is acceptable and that can be stable, but there are some ratios that are not stable. And in this case, if an atom has too many neutrons, what it will do is a neutron in the nucleus is going to eject a high energy electron. And when it does that, it turns itself into a proton. So basically, a neutron, you can think of a neutron as being a combination particle of a proton plus an electron. And it's a neutral particle, so you can see how those charges would cancel each other out and make it a neutral particle. So an electron is ejected from a neutron, and that neutron turns into a proton. So this type of radioactive emission is moderately ionizing. It's not quite as ionizing as alpha radiation, and that is because these beta particles have a single negative charge associated with them. So the magnitude of charge for a beta particle is less than the magnitude of charge for an alpha particle. It doesn't really matter whether it's plus or minus, it's just it's got less overall charge. And it's also smaller. Because it's smaller and it's a high energy electron, it's able to penetrate materials a little bit better than an alpha particle, but it's not quite as ionizing because, one single electron adding itself to an atom somewhere is just ionizing a single thing. Alpha particles, they need 2 electrons, and so they're going to be more ionizing because there's more electrons involved in that. All right, so let's talk about how we balance equations for beta decay. In beta decay, a neutron in the nucleus will eject a high energy electron, turning itself into a proton, which means the number of protons in the nucleus is going to increase. But we're not actually increasing the total number of particles in the nucleus because we're just changing the identity of one. We're just changing a neutron that's already there into a proton. So the mass is going to stay the same, but the atomic number is going to increase by 1. And so if we look at this like a math equation again, we've got uranium-235 equals, or we start out with uranium-235, and then at the end of it, we end up with a high energy electron and neptunium-235, okay, which has 1 more proton. So if we added everything up on this side, this is a -1 because it's showing that is, changing the number of protons in the nucleus. If we add these together, 93 plus -1 is equal to 92. So let's do some examples. So we're going to start here with strontium-90. And we know that it's going to undergo beta radiation, so it's going to give off a beta particle. And when it does that, remember this is some number plus -1 is going to have to equal 38. So how many protons are we going to have here? 39. 39 plus -1 is 38 for the number of protons. And remember, with beta decay, there is no change in the mass. Okay, the next one, we're gonna start off with radium-228. It's going to undergo beta radiation. It's going to emit a beta particle, and we're going to end up with actinium-228. Same mass, there's no change in mass, but our atomic number is going to increase by 1 because a neutron in the nucleus turned into a proton. and then carbon-14 is going to eject a beta particle and become nitrogen-14. All right, so let's see here. The next one is that the next type of radiation we're going to talk about is gamma decay. Gamma decay occurs when a nucleus, or it can occur when a nucleus is really excited and it needs to release a lot of energy. And this is really not something that occurs in everyday situations with gamma radiation. That's a very strong high energy radiation. You might see that, around nuclear reactors or something like that, but it's not something that you come across every day in your everyday life. But it is released when the nucleus is excited. And it's just an energy burst. So if you take a look over here at this, first equation that we're going to talk about, any atom can give off a gamma ray and still be considered that same element. So giving off gamma radiation does not change the identity of an element itself. However, gamma radiation can occur as a result of other changes that occur in the nucleus of an atom. And one example would be called electron capture. So electron capture occurs when a proton in the nucleus, so now here we've got an imbalance in the number of protons and neutrons again, and now we don't have enough neutrons. Now we need more neutrons in order to be stable. So what happens is that proton pulls in an electron from a lower energy level in order to transform itself into a neutron. And this is going to decrease our atomic number. So take a look down here at this picture, and we've got this electron in this energy level that's closest to the nucleus. It's being pulled in by the nucleus here because there's not enough neutrons in the nucleus for it to remain stable. And when it does that, that proton becomes a blue neutron here. And then as a result of that, we've got this empty spot here in this lower energy level, and all these electrons from higher energy levels are going to cascade down to fill in all those empty spots that are created, or that one empty spot that's created here. And when they do that, they can release gamma radiation. Right? It's not always going to be gamma radiation for every type of atom. Maybe for this situation where we've got electron capture going on, but there are electrons that transition between energy levels that we'll talk about next unit. So a gamma ray is a very high energy wave, and they have extremely small wavelengths, smaller than the nuclei of atoms. And they have pretty low ionizing power. And really, it depends on the gamma rays that we're talking about, because gamma rays can, I think, go from anywhere from one millimeter to really super tiny, smaller, less than 10 picometers is what I'm thinking. I'm thinking about something else. So they've got these really tiny wavelengths, and electrons actually absorb electromagnetic radiation, which is light. And that's what a gamma ray is. It's a form of light. We just can't see it. So electrons, when they absorb and they emit that electromagnetic radiation, well, the wavelength here is so small for a gamma ray that it's not likely to knock off an electron off of an atom. All right. So now let's talk about how to balance these equations. We already talked about this. Releasing gamma rays does not change anything about the identity of an atom. It's just an energy release. But when we're talking about electron capture, there is some changes. We talked about how it decreases the atomic number. So let's take a look here. We've got chromium-51. And in this case, we've got the electron on this side because it's being added to the nucleus of that atom. So we want it on this side. They start out as two separate things, a proton and an electron here. So we've got this electron and we've got the nucleus of an atom here described. And we're going to combine those two things and we're going to end up with vanadium-51. So notice the mass number doesn't change because the overall number of particles in the nucleus stays the same. We're just changing the identity. And this time we're going from a proton to a neutron. So we add -1 plus 24 is 23. So vanadium with 23 protons is our answer. So let's go ahead and do some examples really quick. Argon here, argon-38 pulls in an electron into its nucleus, and when it does that, we end up with 18 plus minus 1 equals 17 protons, which happens to be chlorine. And when it becomes chlorine, those electrons cascade down to fill in all those empty spots, or that one empty spot from that electron that was pulled into the nucleus, and they release a gamma ray. Strontium-80 pulls in an electron and becomes rubidium-80. So that atomic number decreased by 1, and a gamma ray is given off. Iodine-125 pulls in an electron and becomes tellurium-125 plus a gamma ray. Thulium-168 pulls in an electron and becomes erbium-168 and a gamma ray. And then Einsteinium-247 pulls in an electron and becomes Californium-247 and a gamma ray. All right, so go ahead and put these examples in your notes if you haven't already done it. It's a good idea to have some examples of these so that you can have something to look at if you need to when you're working on your checkpoint quiz. And now let's go talk about fusion versus fission. Your learning goals for building block 5 are to be able to compare fission reactions and fusion reactions, and these are a type of nuclear reaction. So nuclear fusion is a process in which two small atomic nuclei, come together and they combine to form one larger atomic nucleus. So we're starting out with two small atomic nuclei here, and we're forming something larger. And this generally occurs with elements that are smaller than iron. Okay, so anything smaller than iron is more likely to undergo a fusion reaction. This needs a source of hydrogen as fuel, so what happens here, like an example of where this occurs would be in the sun. And the sun fuses hydrogen into larger and larger elements. And so it can take one of these nuclei and add some hydrogen to it, and that hydrogen nuclei combines with the other nuclei and becomes a larger atom. And so hydrogen is a fuel source that's required, that's used up during this reaction. And another example of where this type of reaction is used is hydrogen bombs. And hydrogen bombs are very energetic. This whole reaction, this fusion reaction, produces, orders of magnitude more energy than a fission reaction would. So this is definitely the more energy dense reaction here. And it produces so much energy that we don't really have the technology to be able to control it. So we can use it for destructive purposes, but we don't have any way of harnessing that energy because there's so much of it at this point. And then nuclear fusion is the process by which one atomic nucleus splits into two smaller atomic nuclei. So we start with a large nucleus, and so on the periodic table, if you're looking where iron is, it's Fe. Anything larger than iron is more likely to undergo fission than fusion. So remember, anything smaller is more likely to undergo fusion. Anything larger than iron is more likely to undergo fission. And this actually is a chain reaction. So what happens here is we've got this really large nucleus, and it has to have some instability associated with it. And we can take advantage of that instability by firing a neutron at that nucleus. And when we do that, that neutron gets in there and throws off the stability of that large nucleus even more, causing it to split into two smaller atoms. When it splits, it produces 3 more neutrons, and those neutrons go hit 3 more atoms, and it just goes on exponentially as an exponential chain reaction. And this type of reaction is used in the atomic bombs. and it's also used in nuclear reactors for power generation. So although it does produce massive amounts of energy, it's not so much that we haven't figured out how to control it. And if you want to watch, I think there's a couple really good videos on this building block. They give you some really good information on, some more examples of where this type of reaction is used. And it also goes into more detail about, how they control the reaction inside a nuclear reactor. So I recommend that you watch those two videos. But this is my last slide for Unit 4. And if you have any questions, remember, go ahead and write them in your notes. I would like to take a few minutes on Monday and Tuesday next week to answer any questions you guys have before we start Atomic Jeopardy.